Welcome back. Um, so the first thing we need to clarify is that I just talked about Zayden doing work on the chair, dragging it across the floor, whereas when he carried the box across the room, I said he didn't do any work. The difference there is that the carrying versus the dragging. When he carried the box across the room, he didn't have to exert a force on it to get it to move sideways. In fact, I got it moving for him and handed it to him while it was in motion and took it away from him before he stopped moving. So he just continued the motion across the room. The difference in the case you just saw is that there's friction present, and thus, when he drags it across the floor, he is exerting a force in the direction of motion. So there is work being done, even though the force is sideways. Um, and so the problem that we saw is when he pulled upward at an angle, he exerted more force, but there was no difference in the experience of the chair. It still moved sideways a certain distance. In fact, it might be that there was less friction. There was less friction. It's not that there might be. There was less friction because he pulled upward on the chair, reducing the normal force and causing there to be less friction. So he actually probably did less work, but there was more force. And we need to figure out, if we just did force times distance, as is the formula we came up with, we need to figure out how to fix the fact that that makes it seem like he did more work by exerting more force, even though it was exactly the same. And he kind of cheated by exerting it at an angle and actually made his experience harder without any difference to the chair. So if we've got the force, here's the picture, the force applied at an angle, the distance traveled sideways. If we label the angle as theta, some of you might have already guessed what the solution is. We need to look at the component of the force Zayden exerted in the direction of motion. And so we could call it F horizontal, for example. And we've got work equals force times distance. But this force needs to be the component of force in direction of motion. And to find that component, what we do is we take the force applied and multiply by the cosine of the angle. So this is just the force applied. And this is the angle between the force and the direction of not direction, but direction of motion. And if we calculate that as the force, then we get a new formula. Work equals force times distance times cosine of theta is the way it's usually written. The cosine of theta comes at the end. And that's actually the accepted common formula for work. Force times distance times cosine of theta, where again force is force applied d is distance through which force was applied, and theta again is angle between force and motion. And that then is our final formula. We're going to look at 4 specific cases to see. Well, we just looked at one. So we're going to look at 3 special cases where we would apply this thing. First, the case where Addie was lifting the box upward. And so she applied the force upward, and the motion was upward. So theta is going to be 0 degrees. The cosine of 0 degrees, or 0 radians, it's the same either way, Milo, is 1. And so our formula becomes work equals force times distance times 1, which is just force times distance, which is exactly what we thought when we had Addie lifting the box up onto the table. So this is box onto table. The next case we'll look at is box across, which has one C in it, across room. In that case, the force is upward, but the motion is sideways. And so the angle there, we have a right angle, so its theta is 90 degrees, or pi over 2 for the purists. And the cosine of 90, or pi over 2, is 0. So we have work equals force times distance times 0, which is 0, which means Zayden did no work in moving the box across the room. The final case we'll look at, and this will just be a hint for something to come later that we'll talk about in class or in another video, is what if we had the case where the motion is this way, and the example I use in class is I push the chair to get it moving and then it slides across the room, and that's the direction of motion, but friction is acting that way. And so in this case, the angle is going to be 180 degrees, or Milo, pi. And the cosine of 180 is equal to -1. So we would have work equals force times distance times -1, which is negative force times distance. So we would have negative work. And we will talk at another time about what that means, but that's significant and something that we'll have to deal with. There's one more thing we have to talk about, which is in all of our calculations, we've been assuming the force was constant. And so if we imagine the case of a bucket of bricks being lifted up to the top of a building, let's say. And so we've got a building, and there's a little pulley and a wheel and doo-doo-doo, and here's a bucket, and or even a bucket of sand, and sand is draining out of the bucket as it goes up. The force being exerted is changing as the bucket goes up. So how do we figure out how much work is done? Because we don't know what force to use to do that calculation. And to figure out, and there are obviously much more complicated cases of force not being constant, but we'll start with that one. And so we wanted to figure out, what do we do if the force changes? That's what that heading says. The final wrinkle, what if the force changes? And what we do is we look at a graph. If we take a graph of force versus distance, in the case of a constant force, the force is the same the whole way. Call it some amount F. And it acts over some distance. Call it D. And so when we take force times distance, what we're actually finding is this is force from here to here. And this is distance, except do it correctly and label it correctly and not backwards. This is distance. This is force. And so I'm multiplying them together, and what I get is that the area is the work. So the other way to calculate work is the area under the force versus distance curve. And a couple of people took calculus last year and saw that this was one of the applications that we looked at in the second semester. Others of you are taking calculus now, and we'll see it later in the semester, but there can be complicated things about finding area under the curve. But this is an important thing, and when we're doing notes in class, I usually tell people put an asterisk in your notebook to mark this spot where you wrote this down, because it's going to be relevant in a lab we're going to do later. And so this would also work if there were a complicated case of some weird, I don't know, if the work was like that to move something. The area here would equal the work done, the area under the force versus distance curve. And we'll do some practice with this, both making graphs and finding the area of simple areas. This curvy thing would be really complicated and would require calculus, but we'll be doing shapes that don't require calculus at all, shapes like this one. In the case of the bucket, for example, if we drew that graph, the force would start out big and then decrease, and let's say it empties by the time it gets to the top. Then we could see this shape, oh wait, that's a triangle. And I know how to calculate the area of a triangle. And so we could figure out the work by looking at the area. So the area under the force versus distance curve is how you deal with both a force being applied that isn't constant, and it works just fine for a force that is constant. And that is the final piece we need to cover, and that is the end of the homework for this time around. Thank you for doing it, and I'll see you in class.